Hello and welcome. So in this video, we want to talk around design loads for structures and really how do we come up with them and what the purpose behind them is. And so for that, want to kind of kick off what our initial thoughts are in terms of how do we approach design of structures. And what we've got here on the screen is that we need to essentially make sure that the demands on the structures in terms of loads, forces, moments are going to be lower than what the capacity of the structure is. And so you can see the little beam I have here, little free body diagram, where we have some distributed load W on a simply supported beam, and that beam has some section size. So it's got some width B and some depth D, and obviously there'll be some material properties associated with that, so some modulus of elasticity, and in some yield stress and some yield strain, etc., etc. And so we'll learn here in some subsequent videos how to determine the capacity. And you've already learned how to work through the statics of this type of problem here. But one of the big questions is, what is this load? How do we determine this load? What is W? Is it something like I've drawn here, where is it really small, and so it might be a relatively small demand relative to the capacity of the beam, or is it something that's really, really big? And how do we determine that? And so that's what in these next few videos we will start talking around. How do we get to this number of W, and how do we relate that to real life actions? So people walking on a structure, it being loaded up with construction materials or traffic, etc., etc. How do we turn that into this sort of uniformly distributed load or some other type of action that we know how to solve? And so in terms of those actions, I think that that's probably a good place to start, is really how do we go from a real life loading to a free body diagram. So I want to show just a few examples here. So the first one would be point load. So this is typical where you'll see most of this is when you've got members framing in. So if you've got this simply supported beam, you can think of that as like a primary beam, and you can think of the two loads P as the secondary beams which are supported by that. And so the forces and the reactions coming from the secondary beams will get transferred onto that primary framing moment. The other times that this could happen is you might have a very large, heavy thing which is loaded up. So you could also consider this like if we thought of the simply supported beam as a roadway, you could think of the 2-point loads as axle loads from a vehicle. So those are a couple really just straightforward examples of where we see point loads in real life. In terms of distributed loads, this is typically, for floors or for roofs. This is the overall gravity load which they're supporting. So that could include the self-weight. And this is really for any member. It's the self-weight because it's uniformly distributed along the length of the member in terms of, you've got some density of the material, and then you have some area of the member. And for most structural elements, we use prismatic elements, so they don't really change their cross-section sizes as you go along them. So that self-weight will be constant. And then in terms of floor loading, this could be, the actual flooring, the carpet, the tiles, and then some spreading out of any loads, which would be content. So that might be office furniture, that might be people, etc., etc. We simplify that as a uniformly distributed load. And then the other note that I have there is that, say we turned this element horizontally, we would effectively, if we're designing for wind pressure, we would simplify that wind pressure as a uniformly distributed load across the face of, say, this being a wall, if we were to turn that beam horizontally. In terms of what we'd have next would be concentrated moments, and it's maybe one where it's a little bit more difficult to think around where would this come in. And I have what's related here is transfer beam. So think a moment is really just any force with any force couple that has some distance. So this could be a really large air handling unit and it's wanting to overturn when it starts up, or like I said with transfer beams, it might be where you have a column coming into the beam and there's not a column below it. And so if that column has a horizontal force, that force is going to create a moment, and a concentrated moment at that. So those are the general ways in which we go from real life loads into these free body diagram simplifications of these loads so that we have something that we can analyze for design. And I think that's an important point to concentrate on, is that these are all simplifications. And that's because for design, we've got, it'd be an iterative process, so there's no point in going in a whole lot of detail to work for something which you'll have to go through many iterations of calculations for, as well as you'll see in the next video, we have a lot of uncertainty around what the levels of these loads are, that there's also not a lot of point in getting too refined in the estimates, because if you think about a floor, it might be full of people, it might have no people, and those people might be of different size. So we have to kind of average all of that out and use some simplification. In terms of other simplifications that we have is, we'll have some point loads, and then we'll, how do we go between this differentiation between using point loads for our analysis and using a uniformly distributed load? Because as you see on the uniformly distributed load drawn there on the right-hand side of the screen, it really is just a whole bunch of point loads just stacked together. And so you can imagine that at some point, these different point loads will effectively act like a uniformly distributed load. Now, we like these UDLs because they're relatively easy to analyze. So we've got some nice closed form solutions. If you wanted to write up a little spreadsheet for it, you have a continuous function there, so you don't have to do step functions and look at, what's the moment on the left side of one point load versus the right side of one point load, and as you move across. And so from a design aspect, what we always want to do is try to simplify the problem so that it's easier to iterate and still give us a good conservative estimate. So the question is, at what point do we go from point loads to UDL? Is it when we have 3 point loads, 2 point loads, 6 point loads? Well, the actual estimate is when we have 4 or more equally spaced point loads, we will treat that as a uniformly distributed load. And that is a common approximation for most structural engineering calculations. To show you a little bit about how that comes around, and so that you don't just have to take my word for it, let's look at the moment diagram distribution for some point loads going up into a uniformly distributed load. So as you can see on the top left, just a single point load, we're getting a maximum moment of about 25 kilonewton meters. And it's a triangular point load distribution, and this is for a force of 10 kilonewtons and a length of 10 meters. And so for the 2 point loads, we've just divided that out by 2, and for the 3, we've divided that 10 kilonewton out by 3. So it's the same total load across here, and we've just distributed it out more. As you can see, as you go to point 2, our maximum moment is reducing. As we have 3 points, we're reducing even further. As we've got 4 points, we're coming down to about 15 kilonewton meters. And then as we get to a uniformly distributed load, we've got a maximum of about 12.5 kilonewton meters. So approximately, these two are starting to behave very similar. Similar distribution of moment, similar maximum moment. Obviously, the 4 point loads is a little bit higher, but as you'll see when we go through the uncertainty in loads, the little bit of difference between 4 point load and maximum moment of 15 kilonewton meters versus 12.5 kilonewton meters is well within the range of tolerance for all of the other levels of uncertainty that we have. And so in terms of a nice iterative design, we will take this 4 point loads, and we will just treat it like it is a uniformly distributed load. So the only point load style analysis that we do would be 1, 2, or 3. And then if we've got 4 or more, we'll just treat it like a UDL. And we'll practice that as we go through looking at different tributary areas and framing in a further video. All right, so now that we know roughly how do we go from loads to a free body diagram representing those loads, we really need to think around, okay, what's going to cause these loads coming in? So if we just go back a slide, we said these were framing loads. Okay, well, how do we know what the magnitude is? What do we know what the magnitude of this uniformly distributed load is, and what are the sources of them? And so one source of load will just be gravity. So gravity on Earth is always acting, and we want to determine, all right, so for that amount of gravity load coming on, what would be, what's going to be what we term permanent load, or sometimes called dead load. And this is really the load of the structure itself, and permanent attachment. So a good way to think around your permanent loads are if you turn the structure upside down, what stays attached. And these won't leave. They're always there, hence the permanent aspect of them. So this might be fixings of internal partitions. It might be the building envelope, so the curtain wall, the exterior of the building, which is keeping the rain and the wind out. And that will be different than, say, our imposed load. So these imposed loads are non-permanent. They can move around, and so that's why we call them live loads. So one of the main live loads is people. And these are, again, all going to be things which are placed on top of the structure, which are non-permanent. So if we turned the structure upside down, these things would fall off. And so that would be people, furnishings. So this would be your office furniture, your desk. If you're in a library, it's the books and all the shelving. If you have a bridge, it's the traffic of both vehicles and pedestrians on the bridge. And so these are going to happen infrequently and at different magnitudes, and can move around to different sizes. So we will have to treat our uncertainty of this a little bit differently than this one. And then the other loads other than gravity loads are what we would call environmental loads. And we've got a few things just sort of written up there. So wind, obviously, wind happens everywhere on Earth, and that will act as a pressure on the building. And as I said in a few slides back, this is going to be a uniformly distributed load. And so that's one of the ones. An earthquake, so particularly here in New Zealand, we have a seismically active country. And so an earthquake load will impose a horizontal load, mostly to the structure, and that will be based upon its inertia, so its mass, and then the acceleration due to the earthquake. Snow load, it's probably more of a problem on some of the areas in the South Island, and this is another sort of type of gravity load, because snow is going to build up on top of a roof and effectively add to our imposed load. But because this happens in sort of different patterns and different magnitudes than our imposed load, we treat it as a separate loading condition, and that's because it has a different amount of uncertainty, which we'll talk about later. Water pressure. So, this is sometimes an issue with buildings, particularly if there's a basement. So water pressure or lateral soil pressure. But really a big issue if we're looking at dams or you're looking at bridges where you are definitely there in a hydraulic flow and the structure is impeding the movement of water. Thermal expansion and contraction. So this is really a big consideration for bridges, which are outside. They heat up all day. They're long. They will expand out. And then at night they contract in. So as they're expanding out, they're going to push against the abutments of the bridge, and that will induce some compression force. And if they're getting cooled down, if they're restrained at the ends, that will again create some tension force there. This is also an issue on large roofs. Again, anything that's going to heat up during the day and expand and then cool down at night and contract, we have to be able to deal with the forces that's going to generate at the restraints. and then, anything else that might occur. And this would be for some specialized applications. So you might think around blast loading. If you are designing an embassy and you need it to resist an explosive charge. You might have impact loading of a vehicle if you're designing a road barrier to keep vehicles from going off the edge of a cliff. So just because these are the only ones I have listed here doesn't mean that they're the only possible sources of loads. But these are sort of the most common ones that we would have for buildings and bridges. But in this class, we're only going to focus on gravity loads. So the environmental loads we will wait until another course, but we can still learn a lot around how do we apply loads and how do we apply them in a design setting, just looking at gravity. So let's break these down a little bit to look at some of the components in more detail. And the first one's going to be around this dead load, so the permanent load. And as I said, it's based upon the self-weight of the structure. And so things that we would count for it, the non-load-bearing partition walls. So these are the walls which divide up a space, but the roof is not supported on. The flooring, so the physical material of the floor, be it concrete, be it wood, be it steel, as well as any furnishings which are on top of that. So carpet, tile, etc. The ceiling, so this might be a suspended ceiling, so like acoustic tiles, or it might be gypsum board. And then, mechanical plant, so, air conditioning units, ducting, plumbing, electrical, and all of that. And for the and then obviously the self-weight of the structure itself, so the beams, the columns, all of that. And to determine the self-weight, what we do is we just take what the specific weight is, so it's effectively its density times the acceleration due to gravity multiplied by its volume. And one of the challenges, particularly on the self-weight thing, is because if you remember back to the beginning of this video, we said that, well, we need to make sure that our structure has, or our structural element has enough capacity in order to resist its demands. Well, if one of those demands comes from just its own weight, one of the challenges at designs, we don't know what size member we're going to use when we start. So to get around that, what we have to do is effectively just guess. And as you get more experienced, your initial guess gets better, but no matter what, you make an initial guess, and then you have to find out, well, what's the loading? So if I say I have a size of an element, say I want something which is a rectangular size, it's 100 millimeters wide and 200 millimeters deep. And then, all right, I need to check what the loading is of that self-weight for the material that I'm using and see, okay, what's the additional self-weight that demand puts on. And then I'll analyze the that little statics problem that includes the imposed load as well as its own self-weight. And then if it doesn't work, I need to change my size. I'll have to probably go to a deeper member or a larger member. And then we just keep in this loop until we have a section size that can carry its own weights. And so that's what I mentioned, that this is an iterative process, and this is why we use so many simplifications. Because we're going to iterate so often, we want relatively simple problems in the design procedure in order to make sure that we can solve these problems in an efficient manner. So in terms of some examples of self-weights, concrete is going to be 24 kilonewtons per meter cubed. This is typically the heaviest thing that we use as structural engineers, mostly because of the volume. Steel is more dense, it's approximately 3 times as dense, but it has a lot more efficient load carrying capacity, and so you'll find that steel buildings are often lighter than concrete buildings simply from that strength to weight ratio. And then the other main material would be timber, and so most pine species are about 4.5 kilonewtons per cubic meter. So we've talked a little bit about how do we determine the self-weight. Let's do an example. So what we have here is determine the self-weight of this concrete beam. It's 30 meters long, it's 700 millimeters wide, and 1.5 meters deep. And we know that its self-weight is 24 kilonewtons per meter cubed. So With that, let's just switch over to our document camera here, and let's draw this out. So we've got a specific weight is going to be 24 kilonewtons per meter cubed. And we've got our little concrete section here. So we'll just draw and it is simply supported. All right, and we'll put some dimensions on here. So it's 1.5 meters tall, 30 meters long, and 0.7 meters wide. Now, we want to draw a free body diagram, so I think what we will do is we'll effectively just start at the end goal, and then we'll just work out what the numbers are. So if we were to analyze this, it has some self-weight, and that self-weight is effectively, it's pushing down just due to gravity. And because this is a uniform section, it's going to have a uniform load. So ultimately what we want to get is a free body diagram between the spans. So we know we want to go between the spans because that's the direction that this is trying to bend itself. So our free body diagram would look something like this, where we're simply supported. We know the span is 30 meters, and we know we have some uniformly distributed load, and that's going to equal W. So right away, we're about halfway through the problem, and we haven't done any math. We've just thought around, okay, this is what our structure is. This is the end goal for our free body diagram. So now, if we want to turn this self-weight and these dimensions into some distributed load, well, ultimately, let's think about the units. We know we need to get into kilonewtons per meter. And so we want to find out, well, what is the weight of this concrete beam for a 1 meter length? So if we think of this as a 1 meter length, what is this weight? And then that's going to be the same weight for that 1 meter, for that 1 meter, for that 1 meter, all the way down. So pretty effectively, all we have to do is work out, well, what's this weight times our cross-sectional area times 1 meter, so per 1 meter. And we would have W equals our unit weight, which is 24 kilonewtons per meter cubed, times our height, 1.5 meters, times our width, 0.7 meters, and that gives us what this 1 meter section would equal. And we can work all of that out. We would get 25.2 kilonewtons per meter, because meters cubed on the bottom, meter times meter squared, that just leaves us with kilonewtons per meter. So W equals 25.2 kilonewtons per meter. Should feel pretty nice and straightforward, hopefully. And because this is a common thing that we do, is we just work out from a unit weight and some cross-sectional dimensions, what is the uniformly distributed load on a beam or on a column. All right, so going back to our slides, that is our permanent loads, so a nice example of those. What about our imposed loads, these live loads, the things that can move around? And as I said, they're anything that can move around on a structure. So just to reiterate, this is people, and this people will be based upon the occupancy type of the building, so whether it's a domestic home or a lecture theater or a hospital or a library. Then it's anything which is furnished in the building, which isn't tied down. So again, the idea, if you turn the structure upside down, anything that falls off is what we would call the live load. And then traffic. And then we determine sort of what they are in a similar manner to dead loads. And we'll see that in the next slides in terms of we've got some assumed weights based upon studies in terms of, how heavy things are and how much space they take up. But one of the big things on live loads is because they can move around, we have to worry about, what's going to be the worst case scenario. So we can't just look at one case of saying everything's all on one span. We might have to look at what they call skip loading, or like the example I have here, we have this truck. Well, this truck could be anywhere along the bridge, and we've got this 300 kilonewton meters. It might be right down here at A. The truck might be going the other direction, and that will change what the demands are on the beams and on this bridge beam and on the reactions as it drives across. So that's one of the big considerations with live loads, or called these imposed loads, is that they can move around, and we will have to consider multiple load cases in order to find out what our worst case is going to be for the structure. Before we start looking at how we calculate these, I always think it's a good idea to get a sense of just how big things are, because we get used to doing all of this math, and we don't, it's always good to have that sort of gut check to like, okay, how heavy is that? Does that make sense in terms of a load which would be applied onto my structure? Just sort of have that reality check. So one thing which I like to do is just think, what is the weight of a kilonewton? What's that in terms of a physical person? And it's your average rugby player is about a kilonewton. It's a big individual, but it's not a huge amount of load in terms of what a structure would carry. So lots of structures can carry one big person. They could carry 10 folks all stacked up on top of each other. They could carry a whole team. So that helps you sort of visualize, per kilonewton, it should be about, an all black hanging off of your structure. The other way for something a little bit bigger is, we're familiar with vehicles. So I've got both the 5th percentile of weight and the 95th percentile of weight vehicles on the roads today in New Zealand and in the US. And so on the smaller end is a Nissan Tita, and that weighs about 11 kilonewtons. So you think around 10-ish kilonewtons, that should be a small compact car hanging off of your structure. And then if you've got a Dodge Ram 2500, it's about, 45, 50 kilonewtons hanging off of your structure. So if you're doing this math and you're looking at sizes and you're looking at loads, just keep that in your head in terms of that reality check to try to anchor what your calculations are relative to what real world elements are, just so you can make sure, does that make sense? If you're finding that you're having a beam fail at 10 kilonewtons, but it's a big heavy concrete beam, it's like, wow, there's bridges which are this size, and they can take many of these little Nissan Titas. Like, maybe I've done something wrong in my calculations. Or on the other way, you might have a domestic house. You're like, well, actually, I can take 700 kilonewtons. Like, well, think around 700 kilonewtons. That's a lot of Nissan Titas stacked up there. Does that make sense in terms of a load? So it's always good to have these reality checks. So that's some just sort of examples of sizes of loads. Now let's have a look at, if we're to design with loads, where do they come from and how do we get them? So what I have here is some design tables from the New Zealand loading standard NZS 1170. So this is a standard which says, basically, because every engineer doesn't have the time or the expertise to go through and do a statistical model of, what's the likely loads to be on, my building. Instead, there's been work done. So for a typical building of a typical use type, here's the loading which would be applied. And so With that, domestic houses are about 1.5 kilonewtons. And that's kPa, and so that would be kilonewtons per square meter, and that's what I've got here. And lecture theaters about twice that. Car parks are about the same. Offices about the same, so about kilonewton and a half per square meter. Again, because I always like having some context for this, a kilonewton and a half per square meter is approximately Shaquille O'Neal. He takes up about a square meter. He weighs 1.5 kilonewtons, so you can think of your domestic house, if you've got like a lecture theater, you can think sort of maybe an 8 meter by 8 meter space. Well, that's going to be 64 shacks with another 64 standing on top of them. In your domestic house, that's rated so you could fill that room full of Shaquille O'Neals, shoulder to shoulder across the whole room. That's the load which it is intended to carry in additional to its self weight. And then also we've got concentrated loads where these might be for any number of reasons. Like for car parks, it might be you have a particularly heavy axle load, and so we will assume that there's 9 kilonewtons on top of that. All right, so let's just do a quick example of basically going from live load. Again, we're going to try to draw a equivalent free body diagram of these cars. So this is our car parking space. It's got 20 meters wide, 30 meters long, and it says that one car weighs 1,500 kilograms, and it takes up a space of 2.5 meters by 5 meters. And then we're just going to assume that we've got everything is uniformly distributed along there. So we want to draw a free body diagram. Again, our slab is spanning this way. Think about, how can we reduce this down to a 2D system? And effectively, we want to take this 20 meter width, bring it down to a line load, and then go to a UDL. So with that, we'll come back to our document camera. And we'll just say, so if one car equals 1,500 kilograms and takes a space of 2.5 by 5.0 meters. Effectively, what we want to do is go from a kilonewton per cubic meter to kPa, and we want to think kPa because obviously that's how we're thinking of these distributed loads. You think of them as kilonewtons per meter squared. So to do that, let's just go with what our weight is. We know that it's 1,500 kilograms, and let's get this into newtons. So it's going to be 9.81 meters per second squared divided by 1,000 newtons per kilonewton, and that's going to equal 14.7 kilonewtons. All right, so now if we want to take kilonewtons and get it into kPa, we'd have 14.7 kilonewtons divided by 2.5 meters times 5.0 meters, and that would give us 1.18 kPa. So effectively what that means is we would have our car parking deck, 30 meters, 20 meters, and it has a force acting down on it of 1.18 kPa over the entire structure. So to go from this to our uniformly distributed load. Because again, we're supported at this end and at this end. And this is 30 meters. Effectively, we want to stack, find out per meter length here how much total load. So effectively what we're doing, much like with our dead load, we're just going to take a 1 meter strip, .0. Let me draw that a little bit better, sorry. 1 meter, yep. So we're going to take a 1 meter strip, and we're going to find out, how much of this load acts in this same 1 meter. Well, all we would do is take our meters, kilonewtons per square meter, and multiply it by one of the dimensions. And so this would give us what our uniformly distributed load is. So if we come across here, we would have W equals 1.18 kilonewtons per meter squared times 20 meters, because over this 20 meters, for this 1 meter length, we know all 20 meters is going to act, and so that would then take us down to W equals 23.6 kilonewtons per meter, and that's this 1 meter length here, and then we know we have that overall 30 meters. So that's effectively how we work out, what these free body diagrams would be with our live load. All right, so with that, that's our introduction to these, different types of design load. And what we're going to see next, and what I'd alluded to a lot in this lecture, was that we don't really know what these loads are. So we have, and they're we've got some uncertainty, particularly around live load. So we need some means to incorporate that uncertainty in our design. And so that's what we'll look at in the next video. But for other than that, thank you for watching.